Welcome back to educator.com and welcome back to linear algebra. Today we're going to be discussing properties of matrix operations. So we've talked a little bit about matrices before. We talked about the dot product. We introduced some linear systems and did a couple of examples. We discovered that we can either have no solution, one solution, or an infinite number of solutions. And now we're going to continue to develop some of the tools that we need in order to make linear algebra more understandable and more powerful, which is ultimately what we want, is we want a toolbox from which we can pull and develop this really powerful mathematical technique. So today we're going to be talking about the properties of the matrices. We're going to be talking about properties of addition, properties of matrix multiplication, scalar multiplication, other things like that. Most of these properties are going to be familiar to you from what you've been doing with the real numbers ever since you were kids. Addition, distributive property, associative property, things like that. Most properties carry over, however, not all properties carry over, and there are a few minor subtleties that we want to sort of make sure we understand and pay attention to so things don't get too out of hand. So let's just jump right in. Okay, the first thing we're going to be talking about are the properties of addition, properties of matrix addition. So let's go ahead and list them out. We will let A, B, C, and D be matrices. More specifically, we want them to be actually m by n matrices. And again, remember that we're using capital letters for matrices, and usually when we talk about vectors, which is an m by 1 or a 1 by n matrix, then we'll usually use a lowercase letter with an arrow on top of it. But capital letters for a standard matrix. So let A, B, C, and D be m by n matrices. Okay. A plus B equals B plus A. This is the commutativity property. In other words, it doesn't really matter which order I add them in. Just like if you add 5 plus 4 is 4 plus 5, matrices are the same thing. And again, we're presuming that these are defined. So if you have a 2 by 3, you need a 2 by 3. You can't add matrices of different dimensions. B, our second property, is the associativity property. So it says that if I add B and C, and then if I add A to it, I can actually do it in a different order. I can add A and B first, and then add C to it. Again, very similar from what you understand with the real numbers. It's perfectly true for matrices as well. Okay, I'm going to introduce a new symbol here. It's a little bit of shorthand. It's a reverse E with an exclamation point. It means there is a unique. So that means there is one. So there is a unique matrix, Rix, 0, and I'm going to put a little bracket around it to make sure that this is the symbol for the 0 matrix, which consists of all entries that are 0. So there exists a unique matrix 0 such that A plus the 0 matrix equals A. And this serves the same function in matrices as the 0 does in numbers. So in other words, 5 plus 0 is still 5. This is called the additive identity. Additive because we're dealing with addition, identity because it leaves it the same. A over here on the left side of the equality sign, A over here on the right side of the equality sign. So it is called additive identity. Or more formally, with these 3 lines here means it is equivalent to, we just call it the 0 matrix. It's probably more appropriate. I'll more often be referring to it as just the 0 matrix or something like that instead of the additive identity. Okay, and our final, okay, once again our little symbol, there exists a unique m by n matrix. We'll call it D, such that, where should we put, let's put it over here. A plus D is equal to the 0 matrix. Call D minus A. So we'll refer to D as minus A. In other words, it's just the reverse. So if I have the number 7, Well, negative 7, 7 plus a negative 7 is equal to 0. It gives me the additive identity for the real numbers. Same way, if I have some matrix A, and if I add negative A to it, I end up with the 0 matrix. Makes complete sense. And again, we're doing corresponding entries. Okay, let's do an example. Let's let A equal 1, negative 2, negative 3, 0, 8, and 7. Okay, and we'll let negative A, which is just the same as negative 1 times A, well, just reverse everything. We have negative 1, 2, 3, and then we have 0, negative 8, negative 7. So when we do A plus negative A, we add corresponding entries. 1 plus negative 1, 0, negative 2 plus 2, 0. Remember, we've already taken care of this negative sign in the entries of the matrix, so I don't have to go negative 2 minus a minus 2. I've already taken care of it. This negative A is just a symbol. These are the entries. So we have negative 2 and 2 is 0. We have negative 3 and 3 is 0. And then we go on to form the 2 by 3 0 matrix. There you go. Now we're going to move on to the properties of multiplication. Let me go back to my black ink here. Okay. Once again, A, B, C are matrices of appropriate size. And if you remember, when we deal with matrix multiplication, appropriate size, when we're multiplying two matrices, let's say, for example, we have, put e.g., for example, if I have a 3 by 2 matrix, and I multiply that, I have to multiply that by a 2 by some other number matrix. These inside dimensions have to match in order for my final matrix to be a 3 by whatever. My final matrix is the outside. So this is what we mean by appropriate. And again, we're presuming that we can do the multiplication, that the multiplication is defined, in other words. So A, B, and C are matrices of appropriate size. Then we have A times BC quantity is equal to AB quantity times C. Again, this is the associative property for multiplication now. I can multiply B times C, then multiply by A. It's the same thing as doing A times B first, and then multiplying by C. I get the same answer. Same as for real numbers. B, A times quantity B plus C. Well, it's exactly what you think it is. This is the distributive property for matrices, and it's equal to A times B plus A times C. In other words, I'm treating these just like numbers, except they're matrices. I'm going to reiterate that fact over and over and over again, and later on when we talk about precise definitions of linearity, when we talk about linear maps in more of the abstract, it'll actually make a lot more sense. As it turns out, matrices and the numbers are actually examples of deeper properties, something called a group property, which those of you that go on into higher mathematics will discuss. It's a very, very beautiful area of mathematics, and the nice thing is that you only have to prove it for one mathematical object called a group, and then you just sort of check to see if these objects that you run across in your studies fulfill the certain handful of axioms, and then, since you've already done all the work, you don't have to do all the work of proving all the theorems for it again. C, A plus B times C equals AC plus BC. That's just the distributive property in reverse. Okay, let's do an example here. Let's take A equal to 5, 2, 3, 2, negative 3, 4. We'll take B equal to 2, negative 1, 1, 0, 0, 2, 2, 2, 3, 0, 3, 0, negative 1, 3. Okay. And let's take C, also a little bit of a big matrix here. 1, 0, 2, 2, negative 3, 0, 0, 0, 3, and 2, 1, 0. Now I have to warn you, from time to time when I write my matrices, I may actually skip these brackets over here. Sometimes I'll just write them out as a square array of numbers. It's a personal choice on my part. As long as the numbers are associated, there should be no confusion. So in case you see that I've forgotten the brackets, it's a completely notational thing. You can actually do your mathematics any way that you want to. You can use symbols, you can use words. It's the underlying mathematics that's important, not the symbolic representation. Of course, presuming that the symbolic representation is understandable to somebody else. Okay, so we have our three matrices here, and let's go ahead and move forward. So we're going to calculate A times BC. Now I'm presuming that you're reasonably familiar with matrix multiplication, so we'll go ahead and just write out, when we do B times C first, and then multiply by A on the left-hand side, we end up with the following matrix: 43, 16, 56, 12, 30, and 8. Now, when we do AB first, and then multiply by C on the right-hand side, well, as it turns out, we get 43, 16, 56, 12, 30, and 8. Now, since we're dealing mostly with just arithmetic and adding numbers, I suggest that you actually go ahead and run through this to confirm that this is true. It is true. One thing that you should note here, notice we did BC here and A on the left-hand side. Here we did AB and we did C on the right-hand side. If you notice, when we were writing down the properties for matrix multiplication, we did not say A times B equals B times A, the way it did for addition. Addition of matrices commutes. A plus B is equal to B plus A. However, multiplication of matrices, A times B is not equal to B times A. And generally speaking, if we do M times P matrix times a P times N matrix, so M by P, P by N, these have to be the same, what you end up with is an M by N matrix. Well, if you reverse those two, if you get N, an N by P matrix, and try to multiply it by an M by P matrix, now P and M are not the same. In this particular case, the multiplication is not even defined. Now, is it possible that if you switch two matrices, you may end up actually getting something that's equal? Possible, if you're dealing with a square matrix. Highly unlikely, but it's not a general case. So commutativity in multiplication does not hold. That's a very, very unusual property. This is one of the properties that's different in matrices than it is in numbers. 5 times 6 is equal to 6 times 5. 5 plus 6 is 6 plus 5. Not the case in matrices. So remember, multiplication in matrices does not commute. So multiplication in matrices does not commute. Very, very important. It has profound consequences, which we'll deal with later on. Okay, let's move on to some other definitions and properties that are associated with multiplication. So let us define an identity matrix. Earlier, we had talked about a zero matrix, which is just a matrix with all 0 entries, and we said that it was the additive identity. In other words, if you add it to any other matrix, nothing changes. You just get the matrix back. In this case, an identity matrix, it is an n by n matrix, so it is square, same number of rows as columns, where everything on the main diagonal, all entries are 1. So an example, the symbolism is something like this. So the identity matrix for 2 is a 2 by 2 matrix, 1, 0, 0, 1. This is the main diagonal right here, from top left to bottom right. This is the skew diagonal. This is the main diagonal. The identity matrix for a fourth dimension is exactly what you think it is. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's a 4 by 4 on the main diagonal. Top left, bottom right, everything is a 1. So that's just the standard identity matrix. Okay. Now, let A be a matrix. The identity matrix of dimension m times A. Okay. Oh, let it be a matrix of dimension m by n, we should specify actually. So we have a matrix m by n. The identity matrix multiplied by A on the left, meaning the identity matrix on the A, is the same as A times the identity matrix of dimension n on the right. And again, this has to do with matrix multiplication. It needs to be defined. This identity matrix is m by m. A is m by n. Therefore, the m's cancel and you're left with an m by n matrix. And the same thing here. A is m by n. Let me write it out. M by n. The identity matrix here is n by n. These go away, leaving you an m by n matrix. So when you're multiplying by identity matrices, commutativity can hold. Next property, let's say we have the matrix A raised to some p power. P is an integer, 2, 3, 4, 5, 6, 7 natural numbers. That's the same as just A times A times A, just p times. Same thing as for numbers. 4 cubed is 4 times 4 times 4. The matrix A cubed is just A times A times A. Again, provided that it's defined. And in this case, A is going to have to be a square matrix. Okay. Very important definition. Just like the definition for numbers, any matrix to the 0 power is equal to the identity matrix. Just like you know that any number, by definition, in order to make the mathematics work, we define any number to the 0 power as 1. 10 to the 0 power, 1. 30 to the 0 power, 1. Pi to the 0 power, 1. Okay. AP, AQ, handle it the exact same way. A, P plus Q. You just add the exponents and multiply it by that many times. So if you have A squared times A cubed, that's going to be A to the 5th. A times A times A times A times A. Just like numbers. There's nothing new here. You're just dealing with matrices. And our last one is A to the P to the Q. Well, you know how to handle this with numbers. You just multiply P and Q. Same thing. A to the P Q. So if you have A squared cubed, that's going to be A to the 6th. A 2 times 3, A to the 6th. There's nothing new here. You're just dealing with matrices instead of numbers. Okay. Couple of things to notate and be aware of. If I have A times B to the P power, now with numbers, you're used to seeing, let's say, 5 times 2 squared. Well, let me write it out for you. 5 times 2 squared. You can go 5 squared, 2 squared. In some sense, you're sort of distributing this 2 over the... With matrices, it doesn't do that. It does not equal A to the P, B to the P. And again, it has to do with the commutativity property. So this is not generally true. It's another property that's not true. When you multiply true matrices and you raise it to some exponential power, it is not the same as raising each one to the exponential power and multiplying them together. That doesn't work with matrices. And again, it has some profound consequences for linear systems and for other deeper properties of linear algebraic systems. Okay. Now, you know that if A times B, if I take two numbers and I multiply them and I end up with 0 for A and B as members of the real number line, this is the symbol for is a member of, and this little r with two little bars here, the real numbers, just the numbers that you know of, positive, negative, everything in between, rational, irrational. Well, this implies you know that either a equals 0 or b equals 0. So again, if I know from numbers that if I multiply two numbers together and I get 0, I know that one of them has to be 0. Let's do an example here to show you that it's not true for matrices. If I take 1, 2, 2, 4, and if I take b equals 4, negative 6, negative 2, and 3, and if this is 2 by 2, AB, I get the 0 matrix. However, notice neither A nor B is 0. So again, for matrices, it doesn't hold. You can multiply two matrices and get the 0 matrix. That doesn't mean that one of them is equal to 0. It's not the same. So keep track of these things that are actually different from the real numbers. Commutativity, this property right here, this property right here, where two matrices can be both non-zero and yet can multiply to a 0 matrix. Another thing that's different is, well, you know the law of cancellation. If I have two numbers, a, b, or three numbers actually, a times b equals a times c, I just know naturally that I can cancel the a. Cancellation property. It implies that b equals c. Well, let's take a matrix. Let's do 1, 2, 2, 4 again. Let's take b equals 2, 1, 3, 2. And let's take a third matrix, negative 2, 7, 5, and negative 1. Now, if I multiply AB, and if I multiply AC, I get the same matrix. I get 8, 5, I get 16, 10. So notice AB, AC, but B and C are not equal. So you can multiply a matrix A by a second matrix, B. You can multiply that same matrix A by a third matrix, C. You might end up with the same matrix. However, that doesn't imply that the second matrix and the third matrix are the same. So another property that's different with matrices that does not follow the real numbers, there is no cancellation property. Okay. Let's move forward. Now we're going to be talking about some properties of scalar multiplication. I'll just go ahead and list these out. We won't necessarily do examples of this because they are reasonably straightforward. You're just talking about multiplying a matrix by a number, which means multiplying each entry of the matrix by that number. Straight, simple arithmetic, no worries. Okay. We will let R and S be real numbers, and A and B matrices. First property, S times A is equal to RS times A. This says if I've multiplied a matrix by some scalar S, and if I multiply it by another scalar, I can pretty much just reverse the multiplication process. I can multiply the two scalars together and then multiply by the matrix. Pretty intuitive for the most part. Nothing strange happening here. B, if I have two scalars that I add together, like 5 plus 2 times some matrix A, that's equal to, distributive property is operative here, RA plus SA. Again, nothing particularly strange happening here. We're just listing the properties so that we have a formality that we've seen them. R times A plus B. If I add two matrices together and then multiply by a scalar, same thing. RA plus RB. The scalar distributes over both matrices. D. If I've multiplied r times if I've multiplied a scalar times some matrix, and then I decide to multiply by another matrix, I can actually reverse those. I can multiply the two matrices together and then multiply by the scalar. Again, these are just ways of manipulating things that we might run across. You'll do them intuitively. You don't necessarily have to refer to these. You already know that these are true. You just go ahead and use them. Okay. So again, we don't have to worry about examples here. They're just arithmetic. Properties of the transpose. Okay. Transpose, very, very important concept. We introduced the transpose before. You remember the transpose is where you take the columns and the rows of a matrix and you switch them. So just as a quick example, let's just say we have a matrix 2, 3, let's do it 3, 2, 1, something like that. We go ahead and we flip this along the main diagonal. Everything that's a row becomes a column. Everything that's a column becomes a row. So under transposition, this becomes 2, 3, 3, 2, 4, 1. What I've done is I've read down the column and I've gone from left to right. 2, 3, that's the first row. 3, 2, that's the second row. 4, 1. All I've done is flip it along the main diagonal. Okay, so now properties, let's say we'll let R be a member of the real numbers. Let's use a little bit of formal mathematics here. And A and B are matrices. Then we have, if I've already taken the transpose of A and then I take the transpose again, it's exactly what you think it is. If I go this way and then if I take the transpose again and I go back that way, I end up with my original matrix A. Completely intuitive. If I add A and B and then take the transpose, I can take the transpose of A and add it to the transpose of B. So A plus B transpose is the same as A transpose plus B transpose. This property is very, very interesting. Something that you could probably expect intuitively, but as it turns out, this property becomes the foundation for the definition of a linear function, which we'll be more precise about later on. There's actually no reason for believing that this should be true. So this has to be proved. In fact, all of these properties, they need to be proven. We won't worry about the proofs. They're all reasonably self-evident, but this one is kind of interesting in and of itself. Okay, this next one is very, very curious. If I multiply two matrices A times B, and then if I take the transpose, I don't get A transpose times B transpose. What I get is B transpose times A transpose. This one, very, very important property. I'll put a couple of stars by it. I mean, all of the properties are important, but this is the one that's most unusual and probably trips up students the most. So when you multiply two matrices and then take the transpose, it's not the same as here. Notice here the order, A plus B first, A transpose first, B transpose, the order is not retained. Here the order is reversed. You have to take the transpose of B first and then multiply by the transpose of A first. That's what makes the equality hold. And then of course our final one, we have some scalar multiplied by a matrix A. If we take the transpose, that's just the same as the scalar times the transpose of A. So you take the transpose first, and then you multiply, as opposed to here you multiply first, which is why we have the parentheses, and do the transpose. Okay. Most of you who are taking a look at this video will probably have some sort of a book that you're referring to. I would certainly recommend taking a look at a proof of this property, property C. It's not a difficult proof. All you're doing is you're literally just, picking the entries of A, multiplying by the entries of B, and sort of doing it longhand. So it is somewhat tedious, if I could use that word, but it isn't difficult. It's completely self-evident. And it's a little bit of a surprise when you actually end up with this. So that's the interesting thing about mathematics, is that things show up in the process of proof that your intuition would not lead you to believe is true, which is why we don't believe our intuition in mathematics past a certain point. We have to rely on proof. It's important, and it'll become very, very evident in linear algebra when we discover some very deep, fundamental properties of not of mathematical structures, but of nature itself that one would not even believe could be true, and yet they are. They're a statement about the nature of reality that you would never even think for a million years might actually be true. Okay, let's do a couple of examples. Let's take a matrix A, and we'll set it equal to 1, 3, 2, 2, negative 1, 3. And again, forgive me for not putting the brackets around it. And I have a matrix B, which is 0, 1, 2, 2, 3, negative 1. Okay, now we want to ask ourselves, we are going to take A times B, we're going to take the transpose, and we want to confirm that it's actually equal to B transpose times A transpose. So what we're doing here is not a proof, what we're doing here is a confirmation. They're very, very different. Confirmation just confirms something true for a specific case. A proof is true generally. Okay, when we multiply AB, I'll let you do the multiplication. This is a 2 by 3, this is a 3 by 2, so we're going to end up with a 2 by 2 matrix. Again, it's just arithmetic, so I'll let you guys take care of that. 7, negative 3, and then we'll go ahead and subject this to transposition. What we end up with is 12, 7, 5, negative 3. Notice the entry, this is a square matrix. The entries along the main diagonal did not change. Everything just switched position. 7 went to 5, 5 went to 7. So that's the left-hand side. 12, 7, 5, negative 3. Now, if I take the transpose of B, which gives me a, well, here. If I take B, if I take the transpose of B, I end up with a 2 by 3 matrix. If I take A and take the transpose of A, this is a 2 by 3, I get a 3 by 2 matrix. When I multiply B transpose times A transpose, 2 by 3 times a 3 by 2, 2 by 3 times 3 by 2, I get a 2 by 2. So it matches. Now we want to see if the entries match. So as far as definitions are concerned, the matrix is defined. When we do the multiplication, sure enough, we end up with 12, 7, 5, negative 3. This confirms the fact that, let's go back up here, A times B, multiply first, and then take the transpose, is the same as taking the transpose of B first, multiplying it on the left of A transpose. Again, this is not random. The order must be maintained in matrix multiplication because matrix multiplication does not commute. In fact, it's often not even defined. Okay. Let's take a look at what we've done here today. We've talked about properties of matrix addition. So very, very similar to properties for real numbers. Matrix A plus B is equal to B plus A. Matrix addition commutes. A plus B plus C quantity equals A plus B quantity plus C. Matrix addition is associative. There is a unique m by n matrix 0 such that A plus the 0 matrix equals 0 plus A matrix. And again, we can do it this way because addition is commutative, is equal to, oops, my apologies here. This should be A. So A plus the 0 matrix leaves it unchanged. So this is called the 0 matrix or the additive identity. We'll call it the 0 matrix most of the time. For every matrix A, there exists a unique matrix D such that when you add D to A, in other words, A plus D, you get the 0 matrix. We'll write D as negative A, which is exactly what it is. 7, negative 7, matrix A, matrix negative A. And call it the additive inverse, or we'll just refer it to as the negative of A. Things like additive inverse, additive identity, these are formal terms that you'll talk about for those of you that go on to study abstract algebra, group theory, ring theory, field theory, things like that. Beautiful area of mathematics, by the way. my personal favorite. Okay, we talked about properties of matrix multiplication. A times B plus C quantity equals A plus B quantity times C. This is the associativity property of multiplication. Notice, there's nothing here about commutativity. Sorry to keep hammering the point. I know you're probably getting sick of it, but matrix multiplication does not commute. It's amazing how many times you actually sort of mention that, and yet we're in such a habit of commuting our multiplication that we don't even think twice about it. We have to catch ourselves. And that's why I keep mentioning it. Distributive property is effective. A times quantity B plus C is AB plus AC. And A plus B quantity times C equals AC plus BC. Now, if we're dealing with a square matrix, n by n, same dimensions, rows and columns, we'll define any matrix to the 0 power is equal to the identity matrix. And again, the identity matrix is just that square matrix where everything on the main diagonal is a 1. Think of it as the 1 matrix, multiplying everything by 1. A raised to the p power, where p is an integer, is just a multiplied by itself p times. We have a to the p power times a to the q power, same as numbers, just raise it to the sum of p plus q. And a to the p to the q power, just multiply p and q. Again, these are all analogous to everything that you deal with numbers. Scalar multiplication. R and S are real numbers, A and B are matrices. R times SA equals RS times A. R plus S times A equals RA plus SA, distribution. Same thing the other way around, R times A plus B matrices, RA plus RB. And A times RB quantity is equal to R times AB quantity. I've covered a lot of properties, but again, most of them are the same, only a couple of subtle differences. Okay, let's take a look at the properties of the transpose, probably the most important. Okay, let R be a scalar, A and B are matrices. A transpose just recovers A. A plus B quantity transpose is equal to A transpose plus B transpose. Order is retained. A times B transpose is equal to B transpose times A transpose. Order is not retained. Highlight that one. Some number times A, then take the transpose, is equal to just taking the transpose of A and then multiplying by that number. Okay, let's see. Let's define 2, 1, 3, minus 1, 2, 4, 3, 1, 0. That's our matrix C. One, 1, 2. Let me make my E a little bit more clear here instead of just a couple of random lines. 2, negative 1, 3, negative 3, 2, 1. And have that. We want to find 3C minus 2E transpose. Just a combination of things. We want to multiply 3 times C, we want to subtract twice E, and then we want to take the transpose of that matrix, if it's defined. Okay. Well, we know that if we have the transpose of some quantity, we can deal with it this way. We can take the transpose individually. And we know that when we have a number times a matrix transpose, we can go ahead and just take the transpose of the matrix first and then multiply by the number. Transpose. Okay. When we go ahead and do C transpose, E transpose, okay, these are 3 by 3, 3 by 3. It's going to end up with 3 by 3 transpose. So 2, 3. Let's go ahead and do it here. Let's do So C transpose, again, we are flipping it along the main diagonal, so we'll end up with 2, negative 1, 3, 1, 2, 1, and then 3, 4, 0, right? And then if we multiply that by 3, we'll multiply each of these entries by 3. We end up with 6 minus 3, 9, 3, 6, 3. 3 times 3 is 9. 3 times 4 is 12. 3 times 0 is 0. Okay, so this is our 3C. And now if we take E, transpose E, we'll get 1, 2, negative 3. I've just taken the columns, switched them to rows. And I have 1, minus 1, 2. And I have 2, 3, 1. So I take the transpose. Now I multiply that by negative 2. Okay? And I end up with let's go, negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. Negative 2 times negative 3 is 6. Negative 2 times 1, negative 2. Negative 2 times negative 1 is 2. Negative 2 times is negative 4. Here we have negative 4 for this entry. Then we have negative 6 for this entry. And we have negative 2 for this entry. Notice what I've done here. This is 3C transpose minus 2E transpose. I could have just done 2 times this and subtracted, but I went ahead and I treated this whole, the coefficient, as a negative 2 to get this. So now what I'm doing is I'm actually going to be adding these straight, okay? Okay, and the final matrix that we end up with, once we add those two matrices together, we end up with 4, negative 7, 15, 1, 8, negative 1, 5, 6, and negative 2. This was 3C minus 2E transpose. We treated it as 3C transpose plus, actually, minus 2 times E transpose. You can treat this, again, you can multiply by 2 and then subtract, or you can actually multiply by the minus 2, treat it as a whole number, and do the addition. You're doing the same thing. Ultimately, it's just about what's comfortable for you. Okay. And that takes care of the properties of matrix multiplication, addition, and transpose, and scalar multiplication. Thank you for joining us at educator.com.